Hi guys, today we're going to talk about 2.2, which is rates of change. We're going to be doing things like finding average velocity on an interval and finding instantaneous velocity at a point. So you are not reading this wrong. We are still going back into section 2.2, which means your assignment is on page 115 again. Hopefully you've bookmarked that from the last couple of assignments. We are doing two different kinds of velocity. So the first one is average velocity. Second one is instantaneous. In average velocity, what that means is that you're starting at one x value and you are going to another x value. So this would be like saying I'm going in a car trip, and at some point I could be going faster, at some point I could be going slower by pushing on the brakes a little bit. But over the whole trip, what is your average velocity? Okay, so that's going to be really similar to like distance equals rate times time type of stuff. The problem is that sometimes we're going to be looking for instantaneous velocity, how fast you're going at one very specific point in time. So that's going to be like x equals some certain number that is chosen in the problem. So there's a difference between the two types of things, and it has to do with slope. Now, we talked in class about what is slope and how is velocity related to that. Let's take a look at the definition of an average velocity, and that's going to help us out here. So first off, we are given a function s. So s is going to show up like all over the place. For some reason, s means position. I am really not sure why they picked s for position. Usually mathematicians pick like certain letters because they go really well with the word, like V for velocity. Really clever, right? So I feel like S has to be like some ancient Greek sort of representation of the word position. I don't know. If you figure that out, like Google it or something, let me know in the next class. I would love to know actually why S is position. Okay, so S of t is going to be your position function most of the time. S represents how far you have traveled. It's like, where do you start? Where do you end? Where are you at certain points in time? Okay, if the object changes position over a period in time, that period of time is called delta t. Remember that delta means a change in, so this would be a change in time. So we would be starting at one time and ending at a second time. If we think about that old equation, distance equals rate times time, which we talked about on the very first day of calculus, rate is the same thing as a velocity. Velocities are rates, how fast something is changing. If you try and solve for r, you have to divide by t. So d over t equals r. Distance traveled is the same thing as saying the change in position. Where did you start? Where did you end? Literally just subtract them. Second thing, t on the bottom is how much time has elapsed. So you take the end time, subtract the beginning time of whatever the interval is. So change in time is delta t. Okay, so this is going to be like S2 minus S1 over T2 minus T1. And what do you know? That sure looks like M, a slope. Like y2 minus y1 over x2 minus x1. So that delta S means change in position. And that's going to be your y values on the graph. And then change in t, change in time. At least they didn't take away the t for time. Okay, so that's going to be like your x-axis. Okay, let's take a look at an example. A tennis ball is dropped from a height of 100 feet. Its height s at time t is given by this position function. So hopefully this makes sense. When t equals 0, if you plugged in 0 right here, you get negative 16 times 0 squared is 0, plus 100 is 100. So s would equal 100 when t equals 0. That's your original starting point, right? Okay, s is feet and t is seconds. Find the average velocity over the time interval. Okay, so average velocity is going to equal the change in position over the change in time. So these guys right here are going to be like your x values, which in this case is time. So this is like x1, no, t1, this cubable, t1 and t2. Okay, so the denominator is going to be 2 minus 1, which should make sense. 1 second has elapsed. On the top there, we need to figure out what is s when t is 2. So it's like s of 2 minus s of 1. What are, I keep writing the wrong thing, s of 1. There we go. So what is s of 2? Well, let's take 2 and plug it in here. We're going to get negative 16 times 2 squared plus 100. So that's going to be negative 16 times 4 plus 100. Negative 16 times 4, what's that? Negative 64 plus 100. So that's 36. Totally should have just looked at the answer key instead of doing mental math. Okay, so the original position of your tennis ball is 100 feet off of the ground. Now, at 2 seconds, we are 36 feet off of the ground. That's what that bit means. Okay, let's do this again, except we'll plug in 1 instead of 2. There, and that number is going to change, and so will that. Okay, so it'll be negative 16 times 1 squared, which is negative 16 times 1, which is negative 16. Really hard math right there. That looks like it is 84. Okay, so at 1 second, the position is 84 feet off of the ground. Hopefully that makes sense. If you start at 100 and then it's dropping, it goes to 84 at 1 second, and then after 2 seconds, it's at 36 feet off of the ground. So the tennis ball is dropping. It's not accidentally like going back up into the air even higher. So those are just little things that you can look for. Let's subtract. We are good at subtracting. On the top, 36 minus 84 is negative 48. And our denominator is 1, which reduces to negative 48. Now, we really have to make sure that we start doing labels anytime there is a word problem or anything related to reality. So let's look at position and time and figure out the labels for those. So position was the numerator. Our position was measured in feet. So the numerator of our label should be feet. Okay, so that's all position. Our denominator, let's do blue on that one, is going to be time. Time t is measured in seconds, so our denominator of our answer should be seconds. And that's it. From 1 second to 2 seconds, our average velocity was negative 48 feet per second. Next example. This time, we are given a table. Okay, the table is telling us t and x of t. Now, this one really annoys me. We talked about s being position. Sometimes they make x of t your position function. It's kind of frustrating, but it is the same thing as like s of t, position. We'll leave it. Okay, so a particle is moving along the x-axis with the following positions. That just means that it's moving sideways. That's all. Along the x-axis means sideways. Okay, so maybe don't think of it as an x-axis, but think of it as like a number line. Okay, so your particle is at 1,5 at some point, and then it goes to 2,7, and then 4,13, and then 6,20, and then 9,25. So the particle keeps moving on to the right. It never doubles back, and you can tell that because these numbers never reverse direction, right? They're always getting bigger. So that generally means that they're always moving to the right. We want to approximate the average velocity of the particle when t equals 5. So let's look at where does t equal 5. That would be the first row, that is time. Where is 5? 5 is halfway in between 4 and 6. Okay, that does not mean that the velocity at t equals 5 is actually halfway in between those. That is not what it means. We are approximating the average velocity. Approximate means guess with a little bit of like theory behind it. You got to give some reasons to your guess. So we are going to use the 2 points, 413 and 620, to help us figure out what probably is about right for the velocity when t equals 5. Okay, so we are going to do some subtraction in here on top and bottom. Let's do it. Average velocity is going to be about, because we are approximating. So it is a fraction. We are finding a slope. It does not matter if we put the 413 first or the 620 first. Let's put the 6 and the 20 first because they happen to be bigger numbers than 4 and 13, which means when we subtract, we're going to get positives. And who doesn't like getting positive numbers instead of negative numbers? All right, so the y value is 20, the x value is 6. The y value is 13, the x value is 4 for calculating slope. All right, numerator, 20 minus 13 is 7. Denominator, 6 minus 4 is 2. So 7 over 2 is 3.5. The average velocity is 3.5 something per something. The problem gave us feet and seconds. Okay, feet was how the y's were labeled. Seconds is how the x's were labeled. And I keep saying x's and y's, but... Okay, so time is in seconds. That's your denominator. And feet is your numerator. That's the position. That's your velocity. What happened here? Okay, we had some weird labeling. I'm going to show you what this is all about. The average velocities are negative. This indicates that the tennis ball is moving blank. Our tennis ball thing was up here. Tennis ball had a negative velocity. We did talk about this. The tennis ball is moving downward. So if you have a negative velocity, downward direction, positive velocity would be moving upward. That's right. All right. Okay. Let's talk about position equation versus velocity. So again, getting into position and velocity. So that S equation, S of t is position. Velocity, how about velocity is going to be V of t? We can be less clever about velocity. Okay, or less creative, I suppose. All right, as we decrease the interval to find the average velocity, we can find the instantaneous velocity of a function at a point. Okay, so what that means is if we start with, this is our actual picture, similar to if you throw something up into the air and then it reaches a peak and then it comes back down and hits the ground, something like that. So we want to know what is the velocity at a very specific point that's instantaneous. So this is like the cop sees you on the road. How fast are you going at this very specific point in time? Now, if the cop figures out how fast what your position is while you're stopped at a stoplight, and then they figure out your position when you're stopped at the next stoplight, and they figure out the time in between, they can figure out your average velocity between those two stops. Okay? But what the cop wants to do is see if you're speeding at one specific point in time. So what should they do? instead of figuring out your time and position at two far away points, they should figure out your time and position for two closer together points in time. So we're going to take a limit as the change in time decreases to 0. So we want, instead of a large amount of time passed, to be a very, very, very small amount of time to pass. And that's what those radar guns do. They figure out very small amounts of time. And they send out a signal to find your position at two very close points in time. So instead of a slope between here and here, hang on, I'm looking at the picture backwards. Instead of looking at a slope from here to here, we would find a slope from here to here. Then we would find a slope from here to here, and then from here to here. So the slopes are getting way closer to the slope of the line at the actual point, slope of the tangent line. Remember that this function with the limit, okay, so that limit of the difference quotient finds, instead of s of t, it finds s prime of t. All right, so that's the same thing as like f prime of x equals f of x plus h minus f of x all over h. But take the limit of that as h goes to 0. Okay, if we swap out h for change in x, which just means the change in whatever this axis is, how far the points are away from each other, we want the change in x to go to 0. That's the same thing that's happening up in this limit that I keep drawing all over. So this is position at a certain time, and when you take the limit, you get the slope of the line at a certain point. Okay, so in other words, velocity, what we've been talking about, v of t or s prime of t, is the derivative of the position function. Right? Velocity is the derivative of position, or velocity is the slope of position. So if you find the derivative of your position function, like you find your s prime of t, you can then plug in a single t value, a single point in time, and that means that you can figure out what was the velocity at one single point in time, instead of up here where we were finding an average velocity between 2 points in time, so over some kind of a time interval. Okay. Let's keep going on this. Velocity is a vector. You probably talked about this in physics this year already. If you haven't talked about it in physics, that I would be very surprised, or maybe you're just not in physics yet. Okay, vectors mean that there is a speed and there is a direction. Okay, so velocity can be positive or negative or 0. Speed, however, cannot be negative. So even if you are running really fast backwards, speed doesn't take into account the idea that you are moving backwards. You're just going like 2 miles an hour or whatever backwards. You're just going 2 miles an hour, and we don't care that you're going in the backwards direction. Okay, but honestly, I think that's what cops do, right? With the radar gun, they don't look to see, are you driving backwards or are you driving forwards? If you're over the speed limit in the opposite direction, they're still going to write you a ticket. And maybe a second one for reckless endangerment, I don't know. Alrighty. So velocity has a direction. If velocity is negative, that means you're going backwards, which on a graph usually means you're moving downward. Are you going to have to use this? I know that's on your mind. No, you're going to be able to take the derivative using your power rule. Every once in a while, you'll use the product rule or the quotient rule, which you haven't learned yet. That'll be coming up in section 2.3. Okay, so you get to use your like S primes and S primes and all that. All right, let's look at this example. At time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. That's this number, the 32. The position of the diver is given by S of t, so the position at time t is going to equal this number. So that means how high up is the person above the water. So S of t is feet above the water. T is how much time has passed. So t equals 0 means that nothing has happened yet, and you're 32 feet above the water. So that's going to look like, if this is t and this is S of t, 0, 32 is right there. Now this is a quadratic. If you did a little bit of effort, you would know that you're going to look like this. It's going to be some kind of a parabola, and this is going to be the water line. Often that's going to be the ground at height 0 or position 0. We want to know for part A, when does the diver hit the water? So what height is the diver going to be when they hit the water? They're going to be here, and S of t is going to be 0. Okay, so when S of t equals 0, they say when. When is a time. So what is t? That's the question. What is t when S of t equals 0? So if you've got the function S of t equals negative 16t squared plus 16t plus 32. You're going to replace S of t with 0 because you know that the height is 0. So negative 16t squared plus 16t plus 32. We want to find out where our function equals 0. If one side of the equation equals 0, you can either factor or use quadratic formula to find t for the other side. It doesn't matter to me which one you use. This one happens to be factorable because you could factor a negative 16 out of all three of those terms. So let's go ahead and do that. Negative 16 gives us t minus, t squared minus t minus 2. Okay, keep factoring. 0 equals negative 16 times t minus 2 times t plus 1. That looks good. Okay. So t equals 2 or t equals negative 1. So 2 seconds after the diver jumps, the height is going to equal 0. Or t equals negative 1 seconds, the height would equal 0. Can we have negative time? No, we are not going back in time. So at t equals 2 seconds, our diver has reached the, oh my gosh, I almost said ground. The diver hits the water, not the ground. I'm going to write that in a sentence. At time t equals 2 seconds, the diver hits the water. This is a super, super common problem. Okay, S of t equals 0 when it says hits the ground, hits the water, something like that. These problems show up all over the place in calculus and physics. Make sure you get really, really good at them. All right, B, what is the diver's velocity at impact? Okay, so part B, I'm going to do this one in purple. What is the diver's velocity at impact? So V of t equals what? That's what it's asking. Okay, so what is the velocity when they impact the water? Okay, so let's find the function V of t. Well, remember that velocity is the same thing as S prime of t. So if S of t itself from up above is negative 16t squared plus 16t plus 32. That was given to us. If you use the power rule, you multiply your power, your exponent times your coefficient, negative 32t plus, and then you remove 1 from the exponent. Remember that one. Next term, 16t's derivative is 16 Last term, 32, its derivative is 0. So our velocity function is v of t, or s prime of t, equals negative 32t plus 16. Okay, but we don't want the velocity function. We want to know what is the velocity at the impact. What's our variable? It's t. Okay, well, when, at what time does our diver impact the water? We found it in the previous section, time t equals 2. So v of 2 is the same thing as s prime of 2, if you want to keep writing that one, which is negative 32 times 2 plus 16, so that's negative 64 plus 16, which is negative, what's that, 48? Okay, so we're going to need from there a label. You cannot just leave it as negative 48. We got to do some labeling. Okay, velocity. Remember that that is a position over time. So what was position measured in? S was measured in feet, so it's feet. Time is t, it was measured in seconds. So the velocity is negative 48 feet per second. The velocity of the diver at impact at t equals 2 seconds is v of 2 equals negative 48 feet per second. So that's the first part of that question. What is the diver's velocity at impact? There's a second question to it, and it says, what is their speed? Remember that speed, they do not care if you are moving in a negative or positive direction. They just care how fast you're going. So the speed of the diver at t equals 2 seconds is 48 feet per second. So speed is the absolute value of velocity. You don't change the sign, you just make it positive. All right, part C, let's do blue for that guy. When does the diver stop moving upward and start their descent? Interesting. Well, let's think about how I drew this and think about what our zeros were for our function. So we know t equals 2, we hit the water, and if the diver had started down low at negative 1, there it is. So it looks like, since we crossed through 0.32, that there is some kind of a maximum that is higher than 32. Doesn't that make sense? Don't divers like jump up slightly and then start moving downward? Absolutely they do. Go watch a YouTube video of a diver. So we want to know, when does the diver stop moving upward and start their descent? So when does that switch over? Well, at a maximum, we know that there is a slope, so s prime of t is going to equal 0, right? That derivative, the slope of the tangent line, is going to equal 0 when you reach a maximum. So we want to know what is t. Switch over to blue again. What is t when s prime of t equals 0? Okay, because of a horizontal tangent. Okay. Well, s prime of t, don't we already have that? S prime of t is the same as v of t. So s prime of t equals v of t, which is negative 32t plus 16. If we substitute out s prime of t for 0, 0 equals negative 32t plus 16. We only have one variable type, t. We're looking for t, so this is perfect. So add 32t to both sides equals 16, and then divide both sides by 32. And you get t equals 1/2. 1/2 what? T. What is t labeled in? T is time. Time is labeled in seconds. So 1/2 of a second has passed, or 0.5 seconds has passed, however you want to write that out. which hopefully makes that sense. Halfway between -1 and +2 is +1/2, and that's going to be where your maximum is. Now that's algebra thinking. This is a calculus course, so you will need to be able to show the calculus idea. But that's not actually that bad to be able to figure out the top point of a parabola. Okay. You are not allowed to just use a calculator and graph this and find the maximum using calculator functions. You have to show your calculus work for this. So I know you can do a little bit of finagling and double check your answers, but make sure you are showing the calculus on this and getting used to it. Alrighty, guys. Go ahead and make sure you get that homework done, page 115, this section. And we'll see you again in section 2.2. 2.3. Oh my gosh, we're not doing any more 2.2.